You're going to get moved here shortly.
Me?
Tate, absolutely not.
Me?
Go. Nope, go. You're about to strike 3. No, I'm talking about all y'all over here, okay? Okay, here we go. You're on strike 2 now. Shh. There we go. Frequencies, not another word. Here is the frequency table that we set up yesterday. We did by 50s, and we started with 75 and went all the way up to 324. And we did frequency of the number of times people had their orders within that time frame. So like we said 2 to 3 minutes was about here, and that was the majority of people, right? Well, not majority. I guess 24 out of 50 is not quite a majority. But like the highest frequency happened in that category, 2 to 3 minutes. Got it? Now, this is just a frequency table. What are these guys called again?
Classes.
Those are classes, okay? And then we have frequencies, which is the number of times that happens over there. Now, I am going to add to this. Listen, because we get to the test and everybody's like, what did that mean again? No, I'm not explaining it to you. Relative frequency and cumulative frequency. This is a normal frequency chart, right? Then we have relative frequency. Relative. Your relatives are the people who live around you. Relative means in relationship to the things around you. What is relative? So when we start this frequency table, I'm continuing this table. This is now one big, huge table. Do you see that? I'm just continuing the column or the columns on, all right? Relative frequency, I'm in this range here, and I want to know if I had 11 as my frequency for that first class. In relationship to all other classes, what is that as a percentage, right? So I would do 11 over 50, right? And 11 over 50, can you convert that to a percentage real fast? 22%. How did she do that? So fast in her head, right?
Use a calculator.
Percent, hold on. Percent is out of 100%, right? And to get from 50 to 100, I just take it times 2. So that would be 22%, all right? This one would be 24 over 50, which would be 48%, about half, a little under half, okay? 10 out of 50 is 20%. 6 out of 50 is
3 out of 50 is
nope.
6.
Nope. Oh, excuse me. 3 out of 50 is 6%. I'm already like trying to do the math already. 2 out of 50 is 4%. Which of those percentages added up to be?
100%.
100%. True? Yes? Okay, but relative means in relationship to all others, like 11 out of the total, 24 out of the total. Yes, ma'am?
Why are we doing this on 50 and not on 100?
Oh, because the total number of people surveyed was 50.
Oh.
Yes, good question. Yes, did anybody else not know where the 50 came from? 50 was the total number of people surveyed. Good question. Yes. Okay, now the last one is called the cumulative frequency. So have you heard the word cumulative test? In typically like December, you take a cumulative test and it is everything you've learned thus far, right? Mm-hmm. Like all the chapters you've learned already, right? Okay, cumulative frequency. So if I'm in the first class, the only cumulative frequency I have is 11. But if I'm in the second class, how many classes or what's the frequency up to that point? 35, okay? The next one, the next class is now 45. The next class is now 48. The last class is now 50. This guy should be your total, right? Now, the reason why this is important is if I were to ask how many people had to wait less than 225 seconds for their order?
11.
225 is here, right? That would be these 3 classes, so 45 people were less than 225 seconds. That's where that comes into comes in handy, right? Do you see how that works? Okay? So that's how that works. Got it? Cumulative frequency. Relative. Relative is in relationship. Relative means percentage. Cumulative is accumulating, right? You accumulate every time you add them going down. Does that make sense? Perfect. All right, next. Okay, here we go. Let's talk about a different frequency table. All right, so we were doing the McDonald's time. Is this McDonald's, right? Yeah. McDonald's delivery times, and we said the highest frequency was here at 24. All right? Have you guys all seen a bell curve?
Yeah.
Yeah, one of these, okay? A bell curve. Boop, right there, like that, right? Okay? Where? What? We did that in algebra, I think. Algebra. We talked about bell curves. All right, here is where a bell curve is generated from, and we'll get to this, okay? From now on, we'll be talking about bell curves and things like that, all right? So let's say here is my classes, okay, and here is my frequencies. And a bell curve generates from your classes in the middle that are the highest frequencies, right? And then they taper off, and then they taper off, and then they taper off. So let's say we're dealing with like height. Okay? This is going to be like your average height. Like the average height of a male is like 5'8" or 5'9", right? You're going to have very few people with frequency that are like 5'2" for males, right? You're going to have very few over here that are 6'2", right? But you're going to have a lot of people high frequency in the middle for the 5'8", 5'9", whatever height for men, right? And if I then draw that as like a linear function, right? And I like lump those all together, it kind of looks like a bell-shaped curve, okay? All right, so let's talk about what this guy would look like if I would draw him, right? So if I would draw him, he has kind of a tall tower 11 here, then we got a 24 tower here, then we've got a 10 tower here, then we've got a 3 tower here, and we've got a 2 tower here. He is not quite bell-shapey curved, right? He is slightly skewed, and he looks more like this. You see that? He is skewed to the right. We'll get to that. It's the opposite of what you think, and the way that you remember that is your foot. Your tall toes like this is your right foot, because your big toe, I'm serious. Literally, you just wait. I'll show you a picture of the feet that they have. There's going to be a foot picture. There will be a foot picture. Oh, but it's not in this chapter. There will be a foot picture.
Yeah, it's in this chapter.
It is in this chapter. Where is it? Where?
It's like at,
It's at the end?
it's at the end.
The foot picture. It's the top right corner.
How'd you know we
There's a foot picture.
I saw it.
Yeah.
What?
Oh my goodness.
Where is it? Is there a foot picture?
Yeah. So it's right past the graphs.
Past the graphs?
Yeah.
Oh, right there! There it is! Look at him. So, right skewed. Here is my right skew. That's my right skew. I'm serious. That's how they write it. So dumb. This is a college stats class, folks. Right skewed. There you go. Okay? He's skewed. The hump is to the left, but he is right skewed. He is there. He's on. Yeah. Whatever. So there's that. Okay? Whatever. So he's right skewed. So now what we will be doing is using these frequency tables to determine the symmetry and determine the distribution. So frequency distribution. Circle that word. Distribution. I want to know how this thing is distributed. Either he is a normal distribution. Okay? A normal distribution looks like a bell-shaped curve where he has symmetric or mostly symmetric. He doesn't have to be exactly symmetric, but mostly symmetric is a normal distribution. Or we have a right skew
Where is that mentioned?
distribution. It's mentioned later on. I'm getting ahead of myself, but it's fine. And a left skew distribution. Okay? And a right skew is the hump on the left, and the left skew is the hump on the right, because it's the opposite of what you think. Okay? Right skew, the hump is on the left skew, the hump is on the right. I don't know, when I taught this last year, I was like, it makes total not sense because it's the opposite of what you think. And Jake Hodson goes, no, it makes perfect sense because the snail is traveling that direction. What are you talking about?
It makes sense though. I get what he's getting at. Because like the shell is
Here the shell and the head, and he's pointing to the right. Here the shell and the head, and he's pointing. I'm like, what are you talking about, Jake? What are you talking about? Whatever. So it wasn't backwards in his backward mind, I guess, or something. I don't know. Whatever. Anyway, right skew, left skew, whatever. So this guy down here, they have a frequency distribution, and what? And here is this. They have redone this with different data, and they said, let's say we had 2, 8, 38, 2. That would be more of a normal distribution where the frequencies, Where the frequencies are starting low, they increase and then they decrease to be low again. Got it? So this is what we're starting to look for. We're starting to use our data, our big data, putting it into classes to figure out what the highest classes are, looking for trends, looking for distributions. Is he symmetric? Is he whatever, right? Skewed right, skewed left. Got it? Okay, all right. Here is some things that we've got to talk about. We've got to address. All right. Here we were talking. Yes, I am. Yeah. Oh, God. What were we just talking about? I don't know. Something funny. All right. How were the pulse rates measured? You guys know that we took pulse rates, and we talked about this when we took pulse rates, but let's see how much you remember. So how were the pulse rates measured? This is the data that I had. They gave me this data after a bunch of pulse rates were measured. Here is how this works. This is the last digit of the pulse rate, meaning this could be 60, or this could be 70, or this could be 80, right? The last digit. This could be 61, or 71, or 81, or 91, right? 62, 72, 52, right? It's the last digit, okay? And they have, hold on, they have frequencies, right? So 455 people recorded something with a last digit of 0, maybe 60 or 70 or 80 or 90 or whatever, right? None of them recorded a last digit of a 1, but a bunch of them recorded a last digit of a 2. So I am getting all of the people have even pulse rates. Does that mean like absolutely nobody has a pulse rate that ends in an odd number? No. Did anybody here have a pulse rate end in an odd number?
They're taking shortcuts. That's what they're doing.
Right. What did they do? How was this data measured?
30 seconds.
Yeah, they only measured 30 seconds. Only counted for 30 seconds, and then what they do? And then doubled. Because when you do that, you will not end up with an odd number. You will only ever end up with an even number. So I can look at this data and say, okay, I get that. That's fine. But I know now that you only counted your data, or you only took your pulse rate for 30 seconds and multiplied it by 2, right? Okay? What? 15 seconds would be 4s. But the problem is, numbers 4 would not just be 4 and 8, right? It would be 2s. It would be even numbers too. So maybe this wasn't 30 seconds. This could have been 15 seconds also.
That's what I said.
Okay. Right, but I'm saying, I thought you were saying that if it was taken every 10 seconds or 15 seconds and multiplied by 4, you'd only have 4s and 8s. You wouldn't. You'd have 12s and 16s and 20s and whatever, right? Does that make sense? Yeah. You would still have the even numbers if you did 15 seconds. So it could be like that, right? Okay. All right, real quick. I'm going to read this. Let's go down here. Nope, let's do this. I'm going to read this bottom part right here. In many surveys, we can determine that survey subjects were reported if the values end in 0 or 5. Okay, so here's the deal. We have another, they don't give us the table. It's somewhere. We'll see it later. But let's say I have this going on. Let's talk about weight. And let's talk about frequency. Do they have this somewhere?
Yeah, it's on the next page.
It's on the next page? Weight and frequency. No, it's not.
Yeah,
No, it's not. Where?
2, 8, right there.
No, I don't want that one. That's not what I want. That's weights of pennies. That's what I want. I'm talking about people's weight. Okay? Weights and frequency. Okay? And this is the last digit of your weight. So 0, a last digit of 1, a last digit of 2, 3, 4, 5, 6, 7, 8, and 9, right? Your last digit. So this person might be 140, or they might be 150, or they might be 160, or they might be 200, right? Their last digit is a 0. This guy might be 133 pounds or 153 pounds or whatever ending in a 3, right? And here's what happens. Let's say I have the frequency that it is 183 people said that they had a weight ending in a 0. None. And 147 people said that they had a weight that ended in a 5 and 0 and 0, 0, 0, 0. Let's say this happens. What is happening here with your weight? Does that just mean that like my scale is broken or something and it's only rounding to the nearest 0 or 5 pounds?
No.
Possibly. What else could be happening?
I guess.
Yeah, I am asking them their weight, right? Unless you're Carter, you need to shut that off. unless you're Carter, because Carter knows exactly like to the 0.75 pounds how much he weighs every day. But if you ask me how much I weigh, I'm probably going to round to the nearest 5 or 10 pounds, right? I'm not going to say like 173 pounds on the nose or, whatever. I'm not 173 pounds. I'm going to lie to you. But anyway. And that was a lie up, not a lie down. But whatever. Anyway. So you're probably going to lie, or you're probably going to round to the nearest 5 pounds if they ask you your weight when you give blood, you might round to the nearest 5 or 10 pounds. So on the 0, on the 5. So you can figure out, judging by the frequency table, how that data-ish, sometimes, how that data was recorded. Got it? Okay, another thing that could happen is that, let's say example 4, here we go, exploring data. We have this thing happening. We're talking about weights of pennies, okay? Like they're weighing a penny in grams. And this is an interesting phenomenon. Here we go. You are weighing a penny. 18 of the pennies had a weight of this. 19 of the pennies had a weight of this. And then I had no pennies weigh that amounts. And then I had some really heavy pennies. I had 2 pennies weighed here, 25 pennies weighed there.
Make the pennies out of a different material.
Yeah.
That's why pennies
We have the presence of gaps. The presence of gaps can suggest that the data are from 2 or more different populations. So I have pennies that were weighed before 1983, which were 95% copper and 5% zinc, and pennies made after 1983 are 2.5% copper and 97.5% zinc, right? So they're made from different materials, and that's showing the gap, right?
Went back, they still had like.
Which one's heavier? Is copper heavier or is zinc heavier? Are pennies heavier now, or are were they heavier before? I think they were heavier before, right?
Everything.
I think copper was heavier, right? So they're lighter now. So copper is a heavier material than zinc. Now they're made mostly from zinc, but they're still painted the copper color, right? Whatever, okay? But these are all before 1983, and these are all my pennies after 1983. What?
They like completely flipped them. It wasn't like 2.5% difference. They like
Hey, look.
to where there was.
I know I saw.
You know what I mean? Like there was
It went
way
from
more
95%
copper than
copper
zinc. Copper to
They just
2.5%.
switched the
Yeah.
ratios.
Oh yeah. Yeah.
I thought it meant-
Yeah. They didn't like even half and half. They like completely did the
Makes me think
materials
if
all
I, like,
weird.
shaved,
Uh-huh.
like, a little layer off of each penny and
Right.
remelted
Right.
it.
Yeah. Yeah.
I'm kidding. But
Yeah. Right.
Maybe I got the-
I think that's illegal, actually, to like destroy money. Like to melt pennies and quarters and whatever. Anyway. Okay.
Probably.
So there you go. Okay.
No, we still smashed these.
Last thing. This is a double frequency table. Double frequency table. And this is showing you 2 frequencies at once. So, you remember my times? My time classes that I had going on here. Here's my times. But now my times are starting at 25 seconds because we're doing another sample, and Dunkin' Donuts is smaller than that, right? So I'm not starting at 75, I'm starting at 25 now. Okay? But now I have not just McDonald's, which was the data that I had before, but now I have Dunkin' Donuts, right? Okay? What's the conclusion that we can draw from having this double frequency table here
Dunkin'
like this?
Donuts is faster.
Dunkin' Donuts is faster. Like the majority of their stuff is happening further, like smaller time increments than McDonald's.
But
McDonald's
would you
is
say
taking
they
longer.
have a shorter menu? A more limit, like a more
Right,
realistic-
and
All
that
their-
probably could contribute.
It's
to
all
it,
just
right?
like drinks.
all their donuts.
Or
are
maybe
pre-made.
people don't like that because maybe that suggests that Dunkin' Donuts has everything pre-made that's sitting out on the counter that's collecting dust and
Maybe
and
Dunkin'
mold
Donuts
and
doesn't
whatever,
have that
right?
as many customers.
So but they're doing it as a relative frequency. So the reason why we converted to a relative frequency is now we're comparing apples to apples, right? Here, if we had 11 out of 50 and we had like 2 out of 10, like of course 11 is going to be bigger than 2, right? Because we're only doing 10 people here. But the fact that we convert them to relative frequencies kind of null and voids that. Does that make sense?
Yes.
Yeah, do you see how that works? We're by converting them both to relative frequency, both to percentages, now I compare apples to apples and not just like 2 different sample sizes.
Got it.
That takes the sample size out of the equation. So if I only surveyed 50 people here and I surveyed 1 million people over here, you're gonna be like, well, of course there's more people like in this category. Well, now that they've converted it to percent, it doesn't matter. Make sense? So percentage wise, I can see that Dunkin' Donuts has